Hi students, this is A. Srinivas, lecturer in physics, Vignan Junior College. Welcome to Vignan digital classes. Now we start ray optics chapter in this video. In previous videos we completed wave optics. Now this is the time to discuss about the ray optics. Ray optics is a very good chapter in JEE Main. It has a lot of applications and a very good number of problems and applications are there in JEE Main examinations. Even in MCET examinations, definitely you got 2 questions from the same chapter. In every year you get an interesting question in JEE Main examinations and equally important in IIT also. In board examinations, in AP board examinations especially, you may get 1 4 marks and 1 2 marks chapter. So in ray optics we discuss about the properties of light. So let us move on to the contents that we discuss in this chapter one after another. Here first one is introduction, second one is laws of reflection. So when light falls on substance like mirror, light may get reflected back into the same medium. Here we are observing light reflected from a rotating mirror. This is the rotating sphere. When light is falling on the rotating sphere, light reflected from it. So this is the reflection. We have to discuss about the laws of reflection, followed by it the sign convention to apply the equations to find out the relation between focal length, object distance and image distance. We have to apply the sign convention, positive and negative signs given to the u, v and focal length values, and followed by the reflection of light by the spherical surfaces. We have concave mirror and convex mirror. In our day-to-day life we use, depending upon situations, concave mirror and convex mirror. For example, all rear view mirrors of vehicles are convex mirrors, and as well as the shaving mirrors in general we use are concave mirror, or mirrors behind the headlights of a car also concave mirror. So we have to discuss about the reflection of light by the spherical mirror, followed by it the mirror equation that gives the relation between object distance, image distance and focal length. Next one is the reflection of light, refraction. Reflection is one phenomena, refraction of light is another phenomena. The refraction of light is explained with the help of Snell's law, and followed by it we discuss about the longitudinal shift and lateral shift. When a light is passing through glass slabs, we observe the shift along the propagation of light along vertical direction as well as along perpendicular direction also. Perpendicular to the direction of propagation, there is a shift in the emergent ray, that is known as the lateral shift. We have to discuss about that shift along the propagation, longitudinal shift, shift perpendicular to direction of propagation, lateral shift. And then the total internal reflection. Total internal reflection is the very important phenomena of light which have plenty of applications in our daily life. Here you are observing a glass slab. When a light is here from this source, we incident the light on the glass slab and it doesn't emerges out from the glass slab, it is undergoing reflection, but there are multiple reflection inside the glass slab. Light undergoes a multiple reflection inside the glass slab. This is due to total internal reflection, and there are so many applications of this the total internal reflection. And next we continue our discussions for the applications of total internal reflection. Here in this image you are observing a optical wire. Through this optical wire the light undergoes total internal reflection for multiple times. Under the total internal reflection phenomena, without loss of its energy, it is propagating with a speed equal to that of velocity of light. So these are some applications of total internal reflection. We have to discuss that applications of total internal reflection. And in nowadays in communication we are transmitting so many number of internet, so many number of waves, communicating waves, and we are utilizing internet in a large way with the help of transmission through optical wires known as internet. Similarly, interconnecting wires between TVs and home theaters, TVs and so many appliances of TVs such as sound bars and home theaters. There is a connection between the TV and their applications by virtue of the optical wires also. And the next one, we go for refraction at spherical surfaces. Means we may have refraction through convex lens, refraction through concave lens, and they are said to be refraction through spherical surfaces, refraction by lenses. Here you are observing in this image, this is the image showing concave lens. Similarly, we have convex lens. So to construct the cameras, to construct microscopes, to construct telescopes, and we use, even in spectacles, we use the spectacles in our day-to-day life to improve our eye power. All these are these camera lenses, telescope lenses, microscope lenses, compound microscope lenses, our spectacle lenses. All those are the lenses through which there is a refraction phenomena, and we discuss about the refraction through convex lens and refraction through concave lens, and power of lenses and combination of lenses, and followed by the refraction phenomena through prism. Refraction through prism. In this image you are observing, this is the light, this is the white light incident on the prism. First it undergoes refraction, then undergoes dispersion, so that white light get divided into its 7 constituent colors from violet to red. You are observing 7 colors on this image. So this phenomena of division of white light into its 7 constituent colors is known as the dispersion. We have to talk about the dispersion and refraction also taking place through this glass prism, and refraction through prism followed by dispersion. See, by the concepts of the dispersion, refraction and total internal reflection, these 3 phenomena are involved in the formation of rainbow. Rainbow is a wonderful picture that we see in the sky rarely during the rainfall and the sun. In the presence of sun and rain in quite opposite positions, suppose sun is rising at east, at the same time if rain is falling at west part, we are in between them, we may observe a wonderful picture in the sky, a naturally formed picture, that is rainbow, which have the phenomena of total internal reflection and refraction and dispersion. These 3 phenomena involved in the formation of rainbow. We have to discuss about the rainbow and scattering of light. So it is our natural observation during the sunset and sunrise, sun appears to be red rather than the white in color. During midday time, sun is white in color. During sunset and sunrise, sun appears to be red. So this is because of scattering of light, as well as we are observing the bluish color of the sky. The sky is in bluish color. That is also due to scattering of the light phenomena, and we have to discuss the definition and phenomena and so many examples of the scattering of light. Next one, optical instruments. The instrument which uses the light passes through them, they are optical instrument. Our eye, this is the schematic diagram of our eye, which has a lens, a convex lens. In front of this convex lens there is a cornea, a pupil, iris, as well as behind the convex lens there is a retina, through which the light signals are transferred to the signals sent to the brain, so we can have a vision, sensation of vision. This is a schematic diagram of eye. Eye is an optical instrument, a natural optical instrument in human body, a very essential organ for us to see the world. Without eye we can't see anything, we can't imagine the world without eye. Eye is a good structure of optical instrument. We have to discuss about eye as a part of optical instrument, as well as the second one is simple microscope, a convex lens that we use as a spectacles, And compound microscope, in general they are used in laboratory to increase the magnification of a very small object, and telescope which are used to see the distinct object. All these are comes under the category of optical instruments. So these are the contents, students, that we have to discuss, okay, in this ray optics chapter. Just I started a new lesson, ray optics. It is very interesting. As we observe the contents, it shows the very interesting contents are there in ray optics chapter. So apart from the subject, apart from the board exams and marks, if you observe the contents, every content is applicable in our daily life, involved in our daily life. Optical instrument eye and lenses, and we are observing dispersion, we are observing rainbows, we are observing scattering of light. Every day we observe ourselves in front of mirror. Mirror shows our image by the phenomena of reflection. Okay, we are using relative mirrors in our daily life. So every content, what I explained, what is present in the ray optics is always connected to us. We use that application in our daily life. That's why it is very interesting. And one more thing, it is a very visualized chapter. So we can see so many animations and visual examples to know about this ray optics very effectively. So let us move on to the introduction of the ray optics. So here the phenomena involved in ray optics are, the first phenomena is reflection. When light is incident on the mirror, or light incident on some surface of water, or light is incident on polished granites, we are observing there is reflection of light. We see our images in water, we see our image in front of a mirror, we see our image in front of a very nicely polished granite. All these are possible to the reflection of light. When light incident on a surfaces like a mirror or surface of water, it come back into the same medium. This phenomena is known as reflection. Here we have to discuss the definition of reflection in coming session. Definition of reflection, laws of reflection, and reflection at plane surfaces, reflection at curved surfaces, and equation involved in the reflection. So this is one example. Here these are the lights placed above the surface of water, and this is Lord Shiva, and we are observing the image of the lights as well as the statue of Lord Shiva. Image of Lord Shiva as well as image of lights, or we are observing their images in the water due to phenomena of reflection. And we have to discuss a deep way of the phenomena of reflection in this chapter. Next phenomena is refraction. Here you are observing this is a glass slab. Let it be in rectangular shape. This is the white light falls on this glass slab. Then it undergoes refraction because actually this white light is unable to propagate along the same direction because medium changes. Here this is the air medium, let this be the glasses medium. When light is passing from air medium to the glasses medium, path of light ray get changed. The change in the path of light is known as refraction. Change in the path of light is refraction. So we have to discuss about the refraction. Along with the refraction, we are observing some colors. This is due to dispersion. Refraction associated with the dispersion. So that here this is the second boundary at which the light ray is traveling from glass to air medium once again. Then also it is changing its path. So that we are observing there is a shift laterally, perpendicular to the slab. Laterally we are observing a shift in the path of light ray. This is known as lateral shift. So a refraction gives the lateral shift, longitudinal shift, and dispersions also. And we have to discuss the definition of refraction and refraction through glassous surfaces, plane surfaces, refraction through curved surfaces such as lenses, and equations involved in the refraction. And next one is the dispersion. So in this animation you are observing, let this be a prism. A prism is having number of boundaries more than 2, in which a transparent medium is bounded. number of boundaries which bounds a transparent medium such as glass is a prism. When white light is incident on one face of the prism, we are getting its constituent colors like VIBGR. You are observing 1, 2, 3, 4, 5, 6, 7 colors. All 7 colors are observing in this animation. VIBGR. So light is divided into 7 its constituent colors. This is known as dispersion. So this dispersion will be discussed. Equations involved in the dispersion and the applications of dispersion will be discussed in this chapter. So next one, the total internal reflection. So total internal reflection. When under certain conditions, when light is allowed to pass into this glass slab under certain conditions, the light doesn't come out from it. It undergoes reflection inside in it. Here we are observing a glass slab, transparent glass slab. When white light is incident, then rose color light is incident in it. It undergoes the phenomena of, see, you are observing a clear image in which light is here and it undergoes reflection. So this is known as total internal reflection. Without loss of energy, light may be transmitted in form of total internal reflection. Applications of total internal reflection. Here you are observing a diamond. There is a glittering of diamond. When light enters into the diamond has ability of glittering, natural glittering is there for the diamond. Once light from outside source enter into the diamond, it doesn't come out from it. That is the specific nature of diamond, because it has so many cuts. So diamond is cut into so many surfaces. You are observing that one. When once light enters from any outside source, light enters into the diamond, it undergoes multiple reflections and it undergoes multiple total internal reflection. This multiple total internal reflection of light inside the diamond gives a glittering, a glorious glittering to the diamond. That's what you are observing here. This is also an example of total internal reflection. We will discuss this application also as a part of applications of total internal reflection. Another one is, another very rarely observed phenomena of total internal reflection is mirage. Students, here you are observing a mirage in which optical illusion, we assume there is water. Actually, there is no water on the highway or in the desert, either on the highway or in the desert. If you observe any farthest position, we undergoes an optical illusion that there would be some water. Actually, there is no water. We assume there would be some water at that present. Here we are observing there is a presence of water here, but actually this is a road, a plain road on which people are walking. But we undergoes an optical illusion that they are walking on the water. There is presence of water. This will happen sometimes during daytime in the presence of sun on hot days, like in desert or on the highways during hot days, hot time when temperature is high. Due to the phenomena of total internal reflection, we observe rarely a formation of mirages. This is one interesting application of total internal reflection. So like that, we have so many plenty applications. And comes to next one. In this animation, you are observing a wonderful rainbow in the sky. So this is possible when there is a rainfall and as well as sunshine at the same time in the sky. At one side, suppose we are standing here at this position. If we stand, and this is the position of the sunshine, and there is a rainfall in quite opposite direction, and the sun rays passes through the water droplets during the rainfall. During rainfall, the sun rays passes through the water droplets, and in that water droplet it undergoes the phenomena of refraction, dispersion and total internal reflection. The combined effort of all these phenomena, refraction, total internal reflection and dispersion, gives a wonderful rainbow in the sky occasionally. This is the animation in which you are observing that rainbow, which constitutes 7 colors. And we will discuss how the rainbow is forming and what is the conditions to have the rainbow. We will discuss very clearly in the coming sessions. And similarly, scattering of light. Here, students, this is the position of sunrise. Over the sea, between two hills, sun is shining. During the sunshine, we observe the reddishness of the sky and reddishness of the sun. Whereas in midday time, the sky is bluish as well as sun is in white color. But during sunset and sunrise, the sky is reddish. And what is the difference? This is due to the scattering. And we have to discuss the applications of scattering to know about the bluishness of the sky as well as reddishness of the sun during sunrise and sunset, which are applications of scattering of light. Like that, there are so many wonderful phenomena and naturally existing phenomena are there. Both these two are naturally existing phenomena. Formation of rainbow during rainfall, during every day, during sunset and sunrise, there is a reddishness of the sky, and during daytime bluishness of the sky. We have to understand, we have to know about what is the reason behind them. And in this way, we have plenty of applications, and as well as the optical instruments. The optical instruments is also very good applications of the ray optics. As I explained, this is the schematic diagram of our eye. So in front of our eye, there is an iris as well as a pupil, and behind that there is a lens in form of convex lens. Beyond that one, there is a retina, which is composed of nerves, which sends the images to our brain, which can identify the visual objects. So there is a wonderful construction, a natural organ existing for us, given by the God is eye. We have to know about the construction and structure of eye. And second one, here you are observing a compound microscope. This is a compound microscope, which are a combination of number of lenses. By arranging the lenses in a proper way, we construct a compound microscope which is magnifies, which is useful to magnification, which magnifies the invisible small insects, invisible small particles can be magnified by 100 or more than that times, so that they are visible for eye. It make visible small objects really not visible are possible to see with the help of compound microscope, which is constructed with the combination of lenses. Okay, this is also one application of optical instruments. As well as here in this image, you are observing a telescope. This is the telescope through which we can see the sky, stars in the sky, and motion of stars, motion of planets, motion of moon, this universe, which is a wonderful combination. The universe can be observed through telescope. Farthest distances like a moon, farthest possible objects like stars, galaxies can be observed more effectively with the help of telescope. To see the farthest objects nearer to us, telescope is helpful. We take aid of telescope. So like that, we have plenty applications of optical instruments. So students, I completed the introduction part, just introduction part of ray optics, which is a very interesting introduction, and very good, fantastic applications are there, and we have to discuss each and every phenomena, each and every application in the coming sessions. So let us move on to the basic definition of light. For all these applications, all applications are done by the light. All applications are useful when light is passing through them. So what is meant by light? What is the definition of light? So light is a part of electromagnetic spectrum of electromagnetic waves. We have electromagnetic waves, and they are divided into several categories known as electromagnetic spectrum. So light is a part of electromagnetic spectrum of electromagnetic waves, which causes a perception of vision. So light or visible light is electromagnetic radiation. Here light or visible light is electromagnetic radiation within the soul. Light is a electromagnetic radiation, a part of electromagnetic radiation within the portion of electromagnetic spectrum that can be detected by the human eye. So that can be detected. We detect the light. Human eye detects. So the part of electromagnetic spectrum which detected by our eye is considered as the light. Usually this light is of wavelength 400 to 700 nanometers. 400 nanometers means 4 into 10 to the power of minus 7 meters to 700 nanometers means 7 into 10 to the power of minus 7 meter. This is the range, wavelength range of light in electromagnetic spectrum. In electromagnetic spectrum, the wavelength range extended from 400 nanometers to 700 nanometers is light or simply visible light which is detected by our eye. We have sensation of vision with the help of this one. Okay, this is the definition of light. And the wavelength less than this 400 nanometers is ultraviolet light. Wavelength more than 700 nanometers is infrared light. So now the ray optics. Ray optics is valid when characteristic dimensions are much larger than the wavelength of light. Here we are observing the interaction of light with the prism. Then the wavelength of light and the dimensions of the prism are compared. The dimensions of prism are much more than the wavelength of light. Similarly, when you observe a light incident on a lens, light incident on a lens like this. Let this be the light incident on a lens. Wavelength of light, compare wavelength of light and dimension of lens. Dimension of lens is nearly 10,000 times more than the wavelength of light. Dimensions of interacting objects like a prism or a lens or a mirror are nearly around 10,000 times more than the wavelength of light. Hence they are useful as the ray optics. In such situations we use the ray optics when wavelength and object size is comparable. Object size is so many number of times more than the wavelength of light, then we use the ray optics. Then we consider the rectilinear propagation of light. As shown here, we use the rectilinear straight line propagation of light like a ray. Hence ray optics is valid. Throughout this chapter we define and explain the phenomena of ray optics under this condition. Okay, let us move on to the first phenomena. The very first phenomena, in introduction I introduced so many phenomena of light that we have to discuss. Already I introduced the phenomena in introduction. Now we discuss each and every phenomena of light in very detail. Now comes to first phenomena named as the reflection. This is the reflection. So when a light, let this be the reflecting surface. So to define the reflection, let this be the reflecting plane, which is coated with hard material at the other end. Suppose this is coated with hard material, painted. Suppose this is painted, this is hard surface. The second surface of the medium is coated with hard material like paint, then it becomes a reflecting surface. When light is incident on this reflecting surface, if light incident on this surface and come back into the same medium, this is known as reflection. Light incident on the interacting surface and come back into the same medium, this phenomena is known as reflecting surface. When a ray of light approaches a smooth polished surface and the light ray bounces back, it is called the reflection. Come back into the same medium. Here the incident ray which lands upon the surface, see the animation, this is the normal. Any line drawn perpendicular to the reflecting surface, this is the plane reflecting surface. A line drawn perpendicular to the plane reflecting surface is named as the normal line. This is the normal line. Dotted line shows a normal line drawn, a perpendicular line drawn to the surface is a normal line at point of incidence. let this be the incident ray. Here we are using arrow marks. So this is the incident ray. Okay. The angle made by incident ray with normal is angle of incidence, let it be I. Okay. And after interaction of the light ray with the surface, it come back into the same medium because of the situation. This is the hard surface here, and from that it get reflected. So the light is reflected. This is the light. If light on incident on this plane surface come back into the same medium as shown in the diagram, this is known as the reflection. This is the reflected light ray. Here this is known as the incident light ray. Incident ray, simply speaking. This is a reflected ray. Reflected ray. First one is incident ray, second one is reflected ray. Angle made by incident ray with normal is angle of incidence. Angle made by reflected ray with normal is angle of reflection. All angles are measured with respect to normal. Angle made by incident ray with normal is angle of incidence. Angle made by reflected ray with normal is angle of reflection. All are measured with respect to normal. So this is the phenomena of reflection. A light ray incident on a surface come back into the same medium, bounce back into the same medium. This phenomena is known as reflection. In case of light falls on any mirror, or sometimes light falls on the polished granite, or light falls on water surface, we observe the phenomena of reflection. So let us move on to the laws of reflection. So to understand the laws of reflection, let us consider the same diagram. Let this be the reflecting surface like a mirror, and here this is the reflecting surface. Let this be a plane mirror, and let us have the normal. This is the normal line drawn perpendicular to the reflecting surface at the point of incidence. Let us consider the incident light ray. Let this be the incident light ray traveling along this direction, and it makes an angle I. This is the angle of incidence, and this is the reflected light ray. Angle made by reflected ray with normal is angle of refraction, let it be R. Now the first law of reflection is incident ray, the reflected ray, normal lie in the same plane. This is the first point. Here you observe, this is the incident ray and this is the reflected ray, and the yellow one is the normal. So incident ray, reflected ray, normal, these three lies in the same plane. This is the first point. And second one is angle of incidence is equal to angle of reflection. Angle of incidence is equal to angle of reflection. Angle of incidence is the angle made by incident ray with normal. Angle made by reflected ray with normal is angle of reflection. Here angle of incidence is equal to angle of reflection. This is the second point. And third one, incident ray, reflected ray generally lie on the either side of the normal. You are observing this is the normal. Incident ray, reflected ray in general lies on either side of the normal. So these are the 3 points shows the laws of reflection. Of course, if incident angle is 0, as I is equal to R, reflecting angle is also equal to 0. In that situation, I and R are 0, then incident ray, normal and reflected ray lie along the same line. Except that I is equal to 0 case, for every non-zero value of angle of incidence, the incident ray and reflected ray must lie on the either side of the normal. So this is about the laws of reflection. Next one interesting and very important point is sign convention of reflection. This is about the sign convention. To apply the equations while solving the numericals, or to derive the equations involving in the reflection, we must use the sign convention. It is the very essential one to move further about the reflection phenomena. So let us consider this is a concave mirror here in this animation. So I explain everything in this part of ray optics in this session as well as in coming session. Every part of our discussion with a beautiful, wonderful animation. So let us see. Let this be a concave mirror. Let us consider. Let this be a concave mirror as shown in the diagram. Okay. and let this be the principal axis. The red line, horizontal line shown in the animation is the principal axis, and this is the direction of light. Let the light ray is incident. We allow the light ray to incident on the mirror from left side. So light ray is traveling towards right. Students, observe the direction. This blue color indicates the light ray and its direction. Light ray is traveling towards right side and incident on the mirror. Okay. Then all distances are measured with respect to pole. Pole is the midpoint. Here let this be the pole of mirror. All the distances, this is the very first point. All the distances are measured with respect to pole of the mirror or optic center of lens. For lenses we have optic center. For mirrors we have pole. So all the distances in the optics are the phenomena with respect to either pole of the mirror or optic center of lens. In general, in mathematics or in any science, we measure the values with respect to origin of the coordinate system. We measure the distances. We measure the heights traveled. Everything is with respect to a coordinate system, that is origin of the coordinate system. That is in mathematics and in science. Here that origin is pole of the mirror. Pole is equivalent to origin, as well as in lenses, optic center is equivalent to origin. In maths and science, we measure the distances with respect to origin. In ray optics, for mirror, we measure the distance with respect to pole. In case of lenses, we measure the distances with respect to optic center of lenses. Here, already we consider this is the mirror. Pole is the midpoint of the geometrical size of the mirror. This is the mirror. Exactly midpoint of the geometrical structure of the mirror is the pole, and the line that passing through the pole and center of curvature is known as the principal axis. This red line, let this red line be principal axis. Let the light be incident in this direction. Light ray is traveling towards right and incident on the mirror as shown in the diagram. Then distances measured towards right side from pole. Distances measured always from pole towards right side, that is in the direction of light. Distances measured along the direction of light, also known as distances measured on the right side of this pole, are positive. Here we are right, these are positive. Whereas distances measured in the opposite direction to the flow of light or transmission of light or traveling of light, distances measured in opposite direction to the traveling of light. See the arrow mark. These distances are taken as negative, which are left side. As light is traveling right side, the leftward distances are measured in negative value. We put negative symbol for them, from measured from pole, and we put negative symbol. As well as vertically upward distances, heights upwards is positive, and this is the general known thing even in coordinate system. We are using same phenomena, and distances measured in downward direction, heights downwards are negative, height upwards are positive. So once again, here if this is the mirror, midpoint of this mirror is pole. Let the light be traveling towards right side direction. Then the distances measured always from the pole, distances measured along the direction of light, that is in right side direction, are positive. Distances measured opposite to the direction of light, that is left side, is negative. The distances measured in upward direction, height upwards is positive, height downwards is negative. These 4 points are said to be the sign convention rules for a total optics. For entire ray optics, either for mirror or for lenses, we use the same thing. But if when you replace this mirror by any lens, the measuring point is replaced, the pole is replaced by optic center of the lens. So let us comes to the very important point, that is spherical mirror. Next one is spherical mirror. So we have 2 types of spherical mirrors, concave mirror and convex mirror. Let us discuss the concave mirror. First one is the concave mirror. We have 2 types of spherical mirrors. One is concave mirror, another one is convex mirror. Let us come to the concave mirror. So this is concave mirror. So if light is incident, light is allowed to incident on concave side of the mirror. Light is coming from left to right. Light is traveling towards right side and incident on this spot. So incident surface is appears to be concave. Hence it is said to be concave mirror. So this is the reflecting surface. If the reflecting surface or light incidenting surface is concave, it is said to be concave mirror. And this is the principal axis, which is passing through the pole. Already I said the midpoint is pole. An axis or a line passing through the pole and center of curvature of the mirror is principal axis. In the diagram we are representing the principal axis by the red line, and this midpoint for the entire concave mirror, this geometrical body, the midpoint of the structure is P, hence P is known as the pole of the mirror. And focus, this is the very important point. Focus is the point at which paraxial light rays converges. The point, the principal focus. If this is the principal focus, the focus on the principal axis is principal focus. Focus on the principal axis is principal focus. And here when paraxial light rays reflected back and converts to a particular point, that point is principal focus, and this is center of curvature. If we extend this geometrical structure, it becomes a sphere. The center of the extended sphere is known as center of curvature. This concave mirror is in form of a curve. This curve is a part of a sphere. So extend the curve and consider a sphere. Center of that sphere is center of curvature. Okay. These are the basic things of any mirror, especially spherical mirror. Okay. Next one, here let us come to the convex mirror. Second type of mirror is convex mirror. Here this is the reflecting surface. See, light incident on the reflecting surface. The reflecting surface is in convex shape. Light incident on the surface which is in convex shape. Hence this mirror is named as the convex mirror. And the axis passing through pole and center of curvature is principal axis. Here the midpoint of the convex mirror is known as the pole, and focus, when light is incident on the convex mirror, in general the light may diverge. So it may appear to be diverging from point. That point is focus, and that is the center of curvature. And this convex mirror is a curve which is a part of sphere. Center of that sphere is known as center of curvature. So for any mirror like either convex, and either side of me you are observing two mirrors. One is concave, another one is convex. Both the mirrors have principal axis, and the geometrical midpoint is the pole. The converging point of the parallel rays or diverging point of the parallel rays are focus. Center of the sphere of this curve is known as center of curvature. So let us define basic definition. Here if you measure the length between center of curvature and the pole, this is known as radius of curvature. If let us observe this animation, students, I am showing the focus with the help of a beautiful animation. Let us consider a paraxial light rays. See, look into the animation carefully. These are the paraxial light rays coming from infinity, which are parallel to principal axis. After reflection, they converge to this point. Okay, very good. This is the converging point. The paraxial light rays incident on the concave mirror and reflected. After reflection, they converge to a point F to form an image. This point is known as focus on the principal axis, hence it is known as the principal focus. Similarly, see, for convex mirror, let us consider the paraxial light rays. These are paraxial light rays incident on the convex mirror, then undergoes reflection. After reflection, they diverge. So this as this is lens, for lens it may move like this. For mirror, they diverge along this direction. They diverge. This is reflection. After reflection, this is the path of light rays. Okay, this is the path of light rays. Then there appears to be there appears to be diverging from this point. Hence, this is known as the focus. There appears to be. After reflection, the light rays moves along this direction, reflected back along this direction. When you prolong or extend it backwards with the dotted line, they converge to this point. So, these reflected light rays appears to be diverging from F. That appearing diverging point is known as the focus. This is the focus of the convex mirror. Okay. So, let us define the basic definition. First one is radius of curvature. The radius of curvature is the linear distance between pole and center of curvature. Here for concave mirror, this is the center of curvature and this is the pole. This distance between these two is radius of curvature. For convex mirror, this is the center of curvature, this is the pole. This distance of separation is known as center of curvature. So let us discuss the second definition. Let us move on to the second definition. Here, a principal axis. This red line is principal axis for the concave mirror, convex mirror, or concave lens or convex lens. The imaginary line passing through the optic center and the center of curvature of any lens. In case of a lens, pole is replaced by optic center. So, imaginary line passing through pole and center of curvature, or imaginary line for lens passing through optic center and center of curvature is principal axis. And next one, pole. The midpoint of the spherical mirror is pole, denoted by P. Next one, the principal focus. The focus on principal axis, or in case of concave mirror, the point to which paraxial light rays are converge after reflection is the point to which paraxial light rays, point to which the paraxial light rays converge after reflection is the principal focus. Similarly, point from which the reflected light rays appears to be diverged, point from which the reflected light rays appears to be diverged from a point on principal axis is the principal focus of convex mirror. That is denoted by F. That is the very important point, principal focus. Here for concave mirror, the principal focus is at the same side of the object, whereas for convex mirror, the principal focus in other side, I denoted F, on other side of the object. Okay. Next one is the definition of focal length. So, for convex mirror or concave mirror, we have the principal focus. Simply, the distance between the pole and the focus, this distance is considered to be focal length, a very important parameter, physical quantity. Here also distance between pole and focal length, pole and the principal focus, distance between pole and principal focus is focal length, F. Of course, in sign convention, it is opposite distance, opposite directed distance, left side measured distance for the right sided directed light ray. So, focal length has a negative sign for concave mirror, whereas for convex mirror, as light ray is traveling in right side direction, focus is also existing in the right side direction, focal length is measured in the right side direction, hence it is positive. So, sign of focal length for concave mirror is positive sign, sign of focal length for concave mirror is negative sign, sign of focal length for convex mirror is positive sign. That is a fixed sign notation. Focal length is F, which is having negative sign for concave mirror and positive sign for convex mirror. Okay, and these are some basic definitions of the mirror. So next comes to some concave mirror. Here this is the principal axis and this is the pole, focus and center of curvature, and this is concave mirror in which we are observing principal axis and pole, focus. This is the pole and this is the focus and this is center of curvature. And when paraxial light rays are incidenting and we are observing focus and they are diverging, we are observing the focus like that. So students, we come to end of this session. Students, especially we started a new lesson, an interesting and a lesson having good visuals is ray optics. we started ray optics chapter, ray optics and optical instruments is the chapter name. We started the ray optics chapter in today class, and in this ray optics chapter, first I introduced the contents, all the contents that we have to discuss in the entire ray optics chapter. I introduced the contents first of all, and also I explained that there are major phenomena like reflection, refraction, dispersion and scattering will be discussed in this chapter, and followed by it, especially in this part of our discussion, I completed the phenomena of reflection and laws of reflection, reflection at spherical surfaces and basic definitions such as focus, pole, focal length, radius of curvature. I introduced the phenomena of the spherical mirrors of two kinds, that is concave mirror and convex mirror. So thank you very much. Thank you one and all.